Okay, we're going to talk a little bit more about the pedigree. We're going to talk about conventions in constructing it, and we're also going to talk about how we use this information. We're going to wrap up with some Punnett Squares, which will mostly be review. It's more about teaching the Punnett Square to people and using it to help them understand their risk. So, some pedigree conventions you want to be aware of always include ethnicity. Certain disorders are more prevalent in different populations. So the correct way to word that question is, where are your aunts, where is your family from? Um, and some people, if their relations have been in America for a long period of time, may have multiple ethnicities. They may have a very diverse heritage, and that's okay. We still want to identify things like Ashkenazi Jewish heritage, because that's affiliated with a lot of recessive disorders, some of them quite serious: breast cancer, ovarian cancer, Tay Sachs disease, Gaucher's disease, a lot of different recessive disorders. And that has to do with population bottlenecks and a limited gene pool, limited biodiversity there, or genetic diversity. Um, Other ethnicities have different risk factors. We know African Americans have a higher risk of sickle cell disease. We know that European Americans have a higher risk of cystic fibrosis and PKU disease. We know that Mediterranean heritage and Middle Eastern heritage increase your risk for certain thalassemias. So it is important to know what someone's ethnicity is in terms of screening for different genetic disorders. You want to sign and date your pedigree. That helps people know who did it and when it was last updated. The book says work in pencil, and that's what I put. But more frequently, you're going to work in a computer tool that has a capacity for editing. The best ones will have things that show you who edited and when, so that you can verify the accuracy of that information. Always indicate your proband with an arrow. Make sure you know where you want to start reading. We're not reading from the top to the bottom or from left to right. We are reading from the proband outwards, from the closest relatives to the furthest away, to calculate their risk. We do a pedigree analysis after we've collected all of the important information and we've recorded it in some visual format, coding for the traits that we want to look more carefully into. Out of all the many genetic traits, you're going to focus on the ones that are the most concerning for this individual. And then you can test that pedigree against possible interpretations. And I have the samples down there, like autosomal dominant, autosomal recessive, X-linked dominant, X-linked recessive, Y-linked, and maternal or mitochondrial. Those are sort of more rare, the maternal mitochondrial disorders, but they do occur. And sometimes, if we know that there's a concern, we can look at the pedigree and determine relative risk. There are actually disorders that have variations, maybe one variation of, let's say, arrhythmogenic right ventricular dysplasia, for example. That is a heart condition. Um, we'll learn about that with cardiovascular disorders. But there are forms of it that are dominant and forms that are recessive. So when we're calculating an individual's risk, we can see how likely it is that they are to be affected by looking at a pedigree. So let's say we have an individual, and this is the pedigree that we've drawn, and he says that somewhere in his family there's some disorder, and he knows that people have died from it. He's not really sure what it is. He's not sure how strongly it runs in his family. So we plot that out on a pedigree, and what we find, we plot the affected individuals in this shaded black, and the unaffected individuals are left blank. So in generation one, the female is affected, marries an unaffected male. They have 4 children. You have your line of inheritance. You have your sibship line here. And you can see individuals number 2, 4, 6, and 8 in generation 2 include the biological children, or are the biological children of this couple. And we've included the people that they mated with. So we have an unaffected female, an affected female. We have an unaffected male and an affected male. So it seems to strike men and women equally, which rules out like an X-linked thing. But it has occurred kind of strongly in 2 successive generations. Let's go to a third generation. Individual number 2 is an unaffected female. She's the couple's eldest daughter. She married an unaffected male and had 2 unaffected children, both genders. Individual number 4 was an affected female, had the disease, married someone unaffected, and had 3 kids, 2 of whom had the disease, 1 male, 1 female. Her 1 daughter was unaffected. Individual number 6 was an unaffected male, married an unaffected female, had 3 kids. None of them had the disease. Individual number 8 was a male with the disease, married an unaffected female. They had 1 child, a male who had the disease. So it occurs in every generation. And it has a fairly good representation, not 50%, because every conception was a toss of the dice. But let's look a little closer at that pattern. If we go to the couple's eldest child, she does not have the disorder. Neither does her partner. Neither do her 2 children. So once that genotype was established, we saw no further emergence of the phenotype in this line. If we were to go 1 more generation, a reasonable assumption could be that none of their children will be affected. When we look at the second daughter, she has the disease. 2 of her children do, even though her mate was unaffected. That's a pretty high incidence in 1 family line. And now it's 3 generations, right? Males and females. Okay, now we go to this child who was an unaffected male, married an unaffected female, and no children in his line had it. So now out of the unaffected people, there are no grandchildren with the trait. But in the people who were affected, each one of those families has a child with the disease. That strongly suggests autosomal dominant inheritance. And the way that it probably looked was that this male was homozygous recessive. This one was heterozygous dominant. She passed on a recessive allele to children numbers 6 and 2, and a dominant allele to children numbers 4 and 8. They married unaffected people who may or may not have, they have no history of the disease, as far as they know. This one had a normal genotype with no copies of the allele, had all normal children. This one had 1 affected copy, dominant, passed it on to 2 of her children. This one had 1 affected copy, passed it on to his son. So that's how that would work, and it's strongly suggestive, though not diagnostic, of autosomal dominant. Now we have this couple, different pattern of inheritance. 2 people without any disease. Okay, the first time this trait that we're interested in shows up in is in generation 3. So we have unaffected male marries unaffected female. They have 4 children, individuals 2, 4, 6, and 8 again. 2 females, 2 males, nobody has a disease. They each marry other people who don't have the disease, but here this couple has a double line indicating they are biologically related, maybe first cousins, maybe second cousins, we don't know. But maybe this is a rare trait, and this couple ends up with 2 children that have the disease. Maybe this is like the couple that I talked about who was from the Honduras. They were first cousins. They denied that there was any family history, but this was a genetic disorder. And they were both carriers. So here's the likely scenario. We have individual number 1 could be a carrier. So 1 dominant copy, 1 recessive copy. Individual number 2, homozygous recessive. They pass on their genes. This person got 1 copy of a recessive allele and 1 copy of a dominant allele. So they were a carrier. She was a carrier. This cousin maybe also had a recessive gene, and the 2 of them combined, passing on 2 copies of the recessive alleles to 2 of their children. The other 2 There's a possibility that they could be carriers. It's a possibility they could be unaffected. We don't know because they are phenotypically normal. It's possible that all of these children are carriers. It's possible that only some of them are, because one allele out of the 4 alleles that could combine during reproduction with this couple had that recessive trait. But none of their children had it. None of them did either. It's very strongly suggestive of autosomal recessive. All right. All right, next. Now we have a male who was affected in generation 1 and 1, 2, 3, 4 males affected by something in generation 3, all males. So already I'm thinking maybe X-linked. And I'm seeing that generation 2 had no affected people. That suggests recessive inheritance. So I'm thinking it's X-linked inheritance. And he married an unaffected female. Maybe she had a copy, or maybe she didn't. Maybe she was homozygous dominant. In that generation, none of the children had the phenotype for the disease. That is because each one of them had a dominant allele that prevented that trait from expressing itself. These 2 females, however, had a copy of the recessive allele, and you can see that because they passed it on to their sons. Remember, when we have X-linked recessive, the daughters usually aren't affected because if that recessive trait were present in the male, he would have it to give 2 copies. So the females are always going to get one dominant X chromosome from mom. So these 2 females were carriers. They gave a dominant allele or a recessive allele, and it was a new toss of the coin each time. So this lady's sons both got the recessive allele. Her daughter may be a carrier or may be unaffected, may have gotten a dominant X chromosome from each parent, or might have dominant from dad and recessive from mom. Same thing in this generation. She passed it on to 2 of her sons. One son was unaffected. He is not a carrier. He only has one X chromosome. So he got the dominant one from his father. He got the Y chromosome from his father. He got the dominant one from his mother, but the dominant allele. Sorry if that sounded confusing. But if you work this out on a Punnett square with any X-linked recessive disorder, you'll see a similar probability of inheritance. This is how it looks actually. And you can see that it's not 50%. It's different. But we do see that males are disproportionately affected. And we do see that it is phenotypically hidden in generation 2. It just suggests autosomal X-linked recessive. All right, so let's try this one. This might be a little tricky. We have in generation 1 a female unaffected, a male unaffected but deceased from whatever cause. Direct line of inheritance. They had 1, 2, 3, 4, 5 children. 3 of their children were unaffected. 2 of their female children, who were identical twins, were affected by the disease. This twin never marries or never passes on her genes. This twin reproduces with a male who does not have the trait. Generation 3, we have nobody affected. So if this gene were dominant and the allele was passed on, the chances are at least one of her children would have it. But in fact, none of the children from this generation do. Most likely, one of these individuals was a carrier. Probably some of these individuals are carriers too. They just did not happen to mate with people who were. And this twin probably mated with somebody who was homozygous dominant for whatever trait that it was. So this looks like autosomal recessive again. All right. You can try that with other pedigrees. It's not diagnostic. It just gives you kind of an idea of how much penetration there is um, in a given family with genes that are affected. And it can be suggestive of dominant or recessive disorders. Using Punnett squares with clients. So you're going to draw the same kind of Punnett square that we did when we talked about patterns of inheritance in chapter 4, week 2. These are diagrams used to determine risk of offspring being affected. If you know the carrier status and the trait transmission pattern, you can draw this diagram, and there's still information you don't have because we don't know how those gametes combined. Uppercase letters indicate dominance, lowercase indicate recessive. We know that. This is review. This would be if we had a, autosomal recessive disorder. The chances of a child having the genotype down here, we worked it out in the square. This is not different from what we did in week 2. So, did you learn? Did you learn how and why to obtain a family history? Did you learn some tools that you can use? Standardized questionnaires, the screen mnemonic. Did you learn when to refer a client or family to a genetic counselor? Could you identify, if you were given a test question, which of the following has a condition that warrants referral to a genetic counselor? If I were to give you 5 choices and it was a select all that apply, do you think you could pick those out? Did you learn the basics of how to construct a pedigree? Sometimes the easiest way to learn it is not to read it and not to listen to it, but to do it. I strongly encourage you to do that. Did you learn the basics of pedigree analysis and interpretation? I don't want you to make yourself crazy with that, but if you look at a pedigree and 5 of the 20 people on it have cancers, and it looks like it's being directly inherited through the line, could you kind of make a case for that? I am going to work on some case studies that will test your knowledge, and then we'll have a RAT after that, a readiness assessment test, and that should put you in good shape. This material will end up on exam 2 for you, will not be on exam 1. Some of it is a little redundant. We kind of covered it in earlier content. But that is enough for now. So have a good week, and I hope you learned a lot.